Hello everybody, my name is Peter Sosala and I will hold the lecture at Reliable Low Latency Communication as part of ComNets 3 now. We hold the lecture a couple of days ago, but the recording did not go that well, so I will just hold it again. First, I will give a short overview about the current wireless networking technologies. The first would be Wi-Fi 6, so the newest version of Wi-Fi or WLAN or 802.11ax. It is made for medium requirement application areas, so soft real time. And the advantages are, for example, the high data throughput and also the low cost. Disadvantages are, for example, that you can't give guarantees in terms of latency. It has a short range depending also on the frequency, and you can suffer from interference with other users because you're working on public bands or called ISM bands. Another technology would be LoRaWAN. It is it is a promising technology for low requirements, for example, in terms of latency or throughput. A typical example are, for example, parking sensors or the sensors you know from the bicycle you can find on the street. When you unlock it, then it opens because the communication works with the LoRaWAN protocol. And advantages are low cost, very energy efficient, and you can use it on over a very long range. Disadvantages are you can't give guarantees and it has relatively high latency. 4G is the mobile uh, mobile communication we are using right now, and it can it can provide a very high throughput, but it's based on the best effort principle. So you can't prioritize, for example, latency critical applications, and it also comes with high costs. So only ISPs or mobile telecommunication providers can pay this price, and no for companies often it's just too expensive. A new technology is 5G, and we are looking into, for example, private 5G. So 5G that a company can buy and use in their own factories. And with this technology, you can integrate different applications with also different requirements in terms of, for example, latency, throughput, reliability. Advantages are low interference from other users because you will buy or you get your own bands um, from the ministry, and with this you can give guarantees more or less as it is possible with wireless systems, and so it can be an enabler for real-time applications done by wireless communication. Disadvantages, for example, could be the complexity, also the currently the high costs in this moment, but it seems like it's getting cheaper and cheaper over the years. And also the range is depending on the data throughput. So if you want to have higher data throughput, you go higher with the frequency, and so the range what you could get, so there's an R over the distance, would fall much faster due to the higher frequencies. So to the applications areas of 5G, there's you can put it into three different areas which are pretty common right now, and this is, for example, the ultra reliable low latency. This is an application area for where real-time communication is very important. This could be, for example, for mobile robotics or wireless industrial communication. The enhanced mobile broadband. This is the one what also was the application for 4G. You should have very high data rates, so very high throughput. And for example, in the application of in factories or on the production sites, you could outsource bandwidth intensive services to a mobile local cloud, so a cloud in your factory, which is also, for example, called mobile, which is often called mobile edge cloud or on the edge cloud. Another application area is the massive machine type communication. These are the parking sensors what I talked before, the high density of devices, often referred as massive IoT, which are often battery life critical, and there are a lot of devices in often big areas, so you have to provide the coverage. And typical applications are, for example, smart cities, logistics, or metering. So, for example, the machines which count your water what you need in your home. More to the application area, as I said before, this you can put there are these three application areas, and you also can see them as a triangle. And as you can see, sometimes the low latency is important, sometimes the mobile broadband, and depending on the application, you can find the requirements somewhere in the middle. And with 5G, at the end, the idea is that it should be possible that different application areas can coexist. And we often focus on three different parameters, which is latency, so also called often as KPI, so key performance indicators. These are the latency, the throughput, and the reliability. And of course, as the name says, what the name says is that for us, if we talk about URLLC, the reliability and also low latency is very important. Now to the use cases. Typical use cases for URLLC are, for example, you can find, for example, in robotics, where you have control streams where you need to react to changes very, very fast. So you have sensors and you have the control system. And between them, you need a very low latency and also very high reliability, because, for example, if you have mobile systems such as AGVs or mobile robots, then they should react as fast as possible to changes in the environment. For example, a person passing the street, and then, of course, it's a safety critical function, so it should react as fast as possible. And if they are controlled from the cloud, you need its low latency. And also, over the time, like AGVs get more and more sensors, and these sensors often provide a lot of data, which also have very strong, very hard latency budget. So the latency budget is in this case a latency that shouldn't be exceeded. For example, 10 milliseconds. Within 10 milliseconds, the AGV then should get a message, and if not, maybe it goes into safety mode and just shuts down. Another thing what's very interesting is the localization of, for example, AGVs. If you go high with the frequency, you can find out the localization of the equipment in a factory. Also by triangulation of different signal sources. Another use case, for example, is surgery, or also referred sometimes as remote surgery, or you can also use like AR applications. For this, haptic feedback is necessary, and of course, this application also has a very low latency budget, but it's their lives on risk. And another use cases could be, for example, autonomous driving, and that could be the vehicle to X communication. What's the or vehicle to infrastructure? Vehicle to X is with something to infrastructure. Could be, for example, traffic lights. When they communicate with the traffic lights to, for example, reduce the speed even before coming near to the traffic lights. Other option would be the communication with other vehicles, so the V2V communication. This one possibility is that, for example, the different vehicles share sensor data or coordinate their future behavior. And this, of course, also should function without cellular networks. And because, of course, self-driving cars are safety critical applications, because they can be also always Crash shouldn't happen. Let's make it short. And another use case that I work on currently is, for example, the 5G campus project, where we want to implement a mobile robot into the Gläsermanufaktur Dresden, as you can see over there. And why a mobile robot? Because you have different requirements. Also, in terms of latency, what would be the control scheme for the HEV or the mobile robot? But also a lot of data which comes, for example, from the LiDAR sensors. And the TOF or time of flight cameras, where you get a depth image about about the area you're looking on, and these LiDAR data then should be processed in a local cloud. And also that the HEV and the robot can be controlled simultaneously, and for this prioritization would be necessary, and we will talk later about this. Prioritization can be done by network slicing, so slicing the network into different priority requirements, or into different applications with different requirements. And as I said before, for this mobile robot, this would be a combination how latency would be combined with high throughput. Since I talked about different applications, what could be possible with 5G, now the question, what's the difference between 4G and 5G? So we often say that we go from human 4G to machines 5G. And the difference is that there's also a requirement change. So if we go to machines, the latency comes into play. And for example, in 4G, we measured 50 milliseconds one-way delay, more or less in optimal environments. So in a room with as little metal as possible. But in reality, it's often 25 milliseconds plus. You can always try it out with, for example, ping app on your phone. You would get, I got like 80 milliseconds. And this is also because, here, as you can see in the right picture, there's the air latency, what could be like around 10 milliseconds, but also the end-to-end mobile latency. This also means all these functions what 4G has to provide. That you could get like latencies about 30 milliseconds up to 50 milliseconds, depending on the structure, depending where's the core. We will talk later about this, located from the telecom provider. And all these functions, for example, in 5G, they were changed. So they were changed with the requirement latency in their mind. And so these end-to-end mobile latencies, this latency of the core function, for example, now also should get reduced. As you can see on the left side, there are the different frequency bands, and with them in relation the coverage band and the latency. And as you know from your studies, the higher the frequency, the lower the coverage. And also the higher the frequency, you will get higher bandwidth to where you will modulate your signal on. And also the latency at the end gets lower, because the faster you can send data, the faster you could get your, let's say, packet through. And so latency can also be reduced. But because of the lower coverage, the low bands, so sub 1 gigahertz is, for example, done for moderate capacity, but you have a very wide area coverage, as we talked before. For example, for LoRaWAN applications, they work sub 1 gigahertz. And the higher the frequency, so the lower the coverage. And these, for example, are for high capacity hotspots like dense urban areas. You can imagine, for example, New York. And now we will talk about the components of a 5G network. You can split it up into the RAN, so the radio access network, and the 5G core network. And the RAN in 5G is called G node B. And the function of a radio access network, of course, is also the transmission of the data between a mobile device, so the UE, they often called user equipment, and the base station. And to do so, there's of course the connection mobility control, and also dynamic allocation of the resource to the uplink and also the downlink. You could say the scheduling of packets for the communication between a user device and the base station. Also other stuff is happening there, the IP header compression, encryption of course encryption of the user data stream, so nobody can look into your private data, and also routing of the user plane, so where data at the end should go, or where to which core it should go, for example, and also measurement and reporting, for example, for the channel quality in this moment, and then depending on the channel quality, data weights, for example, could be changed. And also, of course, the scheduling is influenced. If the channel is worse, then you have to schedule depending on the channel quality. So this also could be changed. And what's happening too right now is functional split. This is because better performance, also more cost effective, if you standardize it, then you could get hardware from different vendors. And there's often a central unit. There are the G-Node-B functions, such as the mobility control, positioning of the different user devices, or localization of the user device, in which radio, with which base station they are connected currently, whether you have handovers to other base stations. Also station management, if a user device connects, then it's registered, and the G-Node-B can communicate with this device, or will communicate with this device. And the distributed unit is the function split you can imagine, all the layer one stuff, so everything what has to do with radio frequency modulation and so on, now is pushed nearer to the user, nearer to the base station. The WAN is getting a bit further, and everything layer one depending things now are as near as possible to the transmitter at the end. And now to the core components. What's at the end the core? You can split it up into three basic functions. There are a lot of more functions, but one, for example, is the access and mobility management function, which is responsible for the authentication and authorization of user devices, also for the registration there, connection management, mobility. As I said before, if, for example, a user moves to another G-Node-B. There's also the session management function, and it has some other functions, but the most important one, UEs get IP addresses from there. UPF, called the user plane function, it is responsible for the packet routing, forwarding, and also the packet inspection. One important thing is there the QoS handling the UPF is responsible for the QoS handling, and also one of the responsibilities is the interconnection with the data network, or you could say the internet, or some network provided from a company, for example. And a short introduction about 3GPP. They are responsible for the standardization of for telecommunications. And currently, we are in the right now we are on release 16, and they started of course with release 1 and release 12, for example. These are the times of 4G. Now since release 15 we are in 5G, and as they show here, 2020 the 5G networks now getting normal in the world, could say it like this. And the release 15 was specified much earlier in 2018, and now release 16 is finished, and we will continue now with release 17. And with each release, there are new functions. But at the end, the equipment vendors such as Ericsson, Nokia, Huawei, they will implement their systems based on the standardization which UPP delivers through these different releases. And now, as we talked a lot now about applications and use cases, and not that much about URLLC. First, we have, of course, define URLLC, or what at the end is, for example, the latency in this case. And the definition of latency for us is the difference between end-to-end delay, or also the one-way delay, and there's a difference to the round-trip time. So if we talk about one-way delay or end-to-end delay, we talk about how long it takes to transmit the data or one packet until the first bit, between the first sending out the first bit and the receiver gets the last bit from one packet between A to B. If we talk about round trip time, it's from A to B and back to A. And for example, in the Ethernet connection, maybe you notice like formula or how the delay, or which are the parts of the total delay in Ethernet connection. There's, for example, the propagation delay. What is the delay for a signal in a physical medium? Also the transmission delay or serialization delay, which describes the time you would need to push all the bits of the data into a wire, and this depends, of course, on the data rate, which is provided by the wire, and also the frame size. So you could say the packet size at the end, what you want to transmit. The queuing delay in this case is the time, for example, the packet spends in a queue waiting until it's transmitted. This can have this delay can cause, for example, in congestion if you send too much data into a link which provides less data than you want to send, so it's getting queued, and so it would get queued. The processing delay can happen because of different reasons. For example, bit hour checking, output link determinations, or the capacity of the link, or also forwarding decision of switch. So processing, if it's software, go to the CPU and back. It's often a bigger problem than everybody imagines. And in a wireless connection, it's a bit different. So in this case, the wireless connection would be from a 5G network, and there's the T-radio, so the transmission time between the user device and the G node B. Additionally, there's the T backhaul delay, what has to be added. This is between G node B and the core network, what normally is, for example, fiber and some switches in between. So these also add delay. Then the delay from the core. What is the processing time in the core functions? And for example, which parts are influenced? This could be the AMF, could influence this delay. This could be, for example, the AMF and the UPF. The delay from the transport in this case could be, for example, from between the core network and the internet. So if you want to Google something with your mobile phone, it will go out into the data network as we showed before. And these would be the latency what would be added after the core until the servers from Google. And as we, what's one of the most important delays, of course, is the radio, the delay added by the the time you need to transfer the packet from the user device to the G node B. And these you can split up into the queuing delay, the frame delay, transmitting delay, and also the processing delays. In this case, the queuing delays is you have to wait until you can send, until you get your slot, and this of course depends on the number of users. Then you would have the frame delay. This depends on the frame structure. So this is the delay until you get your until you get a frame where you can send on. And the transmitting delay is that you need a place in a frame. So this is also called minimum time transmission interval. So this, for example, depends on the radio channel condition, the size of the payload, also the available resources, transmissions, or errors, and also retransmissions. And this is, for example, one thing you can, for example, lower the TTI, but we will talk later about this. And of course, you always have to add the processing delays, in this case from the G node B and also from the user devices. And what's the reliability? And the reliability is always defined as the probability that the data of size D is transferred within a time period T, what we also could say, what we also could call, for example, latency budget. And in a communication setup, reliability can be defined as the probability that the latency does not exceed a deadline. And for example, outage means in this case that the probability is exceeded. And this probability, you can see here the probability of a link or a setup to deliver packets within a time X. So at the end, you could say CDF. And in this case, this probability is defined by the probability of a packet loss or a packet error, as you can see here. And for ultra reliable low latency communication, you could say it's 3GPP defined it as 1 minus 10 to the power of 5, or you could say 99.999% of the packets should be delivered without exceeding this latency budget or within this time period T. And you can see this, for example, in requirements set by the 3GPP. You can see here the end-to-end latency, also the jitter, and the reliability. So the end-to-end latency of 5 milliseconds in this case is the reliability is even higher than defined before for URLLC for different use cases. In this case, for example, the tactile interaction is exactly the reliability requirement for URLLC. And if you would say run to time of 1 millisecond, the end-to-end latency would be 0.5 milliseconds. For the electricity distribution, a higher end-to-end latency, but also a much higher reliability is required or specified. And what could be, for example, typical reasons for packet error or loss? Of course, this could be the distance or a lower SNR. This depends on the frequency, as we said before, as I showed before, and also fading, for example, because of reflection, often a problem in areas where a lot of metal is, where you have a lot of metal, for example, in production sites. Also, if there's, for example, no line of sight or between the transmitter and the receiver. And another big problem could be the interference from other users, and how we could beat it, or how we could address these problems. As you can see here, there are different enablers for your LC. This, for example, is a very good source. I got it from there, and if you're interested in this topic, you can read some basic. You can find like the basic informations about the URLLC topic, or also about latency and reliability in this source. And typical enablers are, for example, the short TTI. Why, if you have smaller time transmission interval, you can put your data faster in it. So it's always, you can imagine it as a cycle, frames are sent out, and if these frames are getting smaller or if they get a higher frequency at the end, of what it means, then you could send it faster and the latency gets smaller. And another important thing, for example, is densification, so more base stations, and so you have a higher availability. You also, of course, need more base stations if you have higher frequency, as I described before. Also UAVs could help, then mobile edge cloud, we will talk about this, of course, coding, there are different machine learning ideas based on machine learning, for example, to get to the low latency communication. The reliability part is the HRQ, what at the end means that you send data again. So if you have packet losses, you find it out and you request packets again, and often these are encoded. So of course, codes again help a lot. Packet duplication, so adding redundancy also for coding, multi-connectivity, again network coding and network slicing. And to put this all together, also one good thing would be, for example, the grant-free transmission. So you know, right now, if a user device wants to send something, it needs to request a slot from the base station. This takes time, and right now there are ideas to just give their slots without any permissions of the base station, pending, for example, to learn the load user device wants to send. And just as an example, densification and also cooperation between different base stations. As you can see at the left, there's the average latency of the users depending on the base station density. And as you can see, the more base stations in the area, the lower the average latency. And there are three different types. And one is, for example, if the base stations cooperate. This could be if they exchange data signals and informations in between them, and so you can cancel interference, and you also could prioritize the transmissions of, for example, identified low latency users. And at the end, what you would win through network densification, you would increase the signal to interference plus noise ratio for all users, and therefore you can see the more base stations, the higher the lower the average latency, and if they cooperate, you can get lower than in the case they don't cooperate. Another promising technology to reduce the latency in the core network is, for example, network slicing. This would be done by prioritizing different data streams, and you, for example, give guarantees for bit rates for example, low latency data streams. SDN is, for example, SDN is an enabler, and it is it's a widely accepted technique to implement network slicing, which then would be implemented on the basis of network function virtualization. In this source, for example, you could get a good description if you're interested into this topic, and with network function virtualization, you could replace traditional network elements, for example, the mobility management entity and also the packet service gateway from the 4G network, and get it more flexible through the softwareization. And I talked before also about the edge cloud, and for the edge cloud, the basic idea to bring the latency sensitive services near to the user. And the enhancement is the mobile edge cloud, where, as you can maybe imagine for mobile, the service moves with the user and the network. So if the user changes the base station, the edge cloud, or in this case the mobile edge cloud, follows the user. So the service is always available in each base station the user connects to. And as always, of course, we have trade-offs. also in this case, and as you can see on the left, if you, for example, want to increase the throughput, you will go to the best effort principle, and G reliability will fall, and also a result also would be an increase in the latency. But if you, for example, want to have a high reliability and also low latency, the throughput would get lower. And these, for example, the reasons are: if you add more redundancy to gain a higher reliability, this will result in a higher average latency because of decoding and coding, for example, and also to a lower throughput, so because of the lower information or coding rate. And as we said before, smaller stop length would result in this case in lower latency, but also on a lower throughput because of synchronization in between, and also, for example, because of headers what would have to be sent. And to the hands-on, some of you already maybe had it, and yeah, you now heard about all these requirements and what would be possible in the 5G system. But are these processes really time critical? And therefore, we made the hands-on. We created some practical experience through the hands-on, and there you will control a pendulum through the motion controller, which then, in this case, the pendulum is the actuator, and these then will sense their current state and give it back to the motion controller. We will add the latency here and there, and you will find out how is the influence of the latency to the system. And we will do this with the QuanzaCube Servo 2, and at the end is as you can see at the right, the pendulum, and you will control it at the end of the controller and the edge cloud. And what will you learn? Some basic control theory. What happens if the controller and processors are physically distributed, and then what happens if we add the latency? What will happen? This we will find out. And yes, as you can see, these are the dates, and no lecture on the 10th of November. There you had or will have a hands-on session. And please download the hands-on document and solve the preparation task before going. So thanks a lot, and some information what you should have learned in this course. This would be, for example, where does the latency come from in a wireless link, maybe also in the Ethernet link, and how you can tackle it, and maybe some use cases and why it's important. So thanks a lot, and have a nice day or evening.